Hi, our topic for today is permutations. Permutations are a special configuration and that we should know how to recognize. So what is about certain configuration that makes it a permutation, and then we need to learn fairly easy formula to help us to count them and then see how do we kind of do the adjustments of that technique to different problems. So let me write the theorem first. So theorem says, theorem 4.1. Oh, actually, I cannot give a run around the theorem before I say what it is. So what is P of n? Configuration P of n. So permutations of n elements. So what is this? It is a list of n elements. So elements are on this example 1, 2, 3, 4, 5, 6. So that all 6 elements are in the list, but in different orders. So for example, 5, 3, 4, 1, 2, 6. So this is one permutation of these 6 elements. So permutations of n elements are all possible orders, or all possible lists of n elements. With no repetitions. So generally, whatever we learn in this section and the next one, I will ask you 3 questions. So a repetition, all in order important. So we answer here repetitions. No. Are all the elements in? Yes. Is the order important? Yes. So that's what describes basically this configuration. And the theorem 4.2.1 says the following: P of n, there's a cardinality there. P of n is just a number. So let's say P of n is just that set of configurations, and P of n is their count, so P of n is the number, so P of n equals n factorial. Maybe you saw this math notation, maybe you didn't. What is n factorial? Product of all the numbers from n down. So n, n minus 2, n minus 1, n minus 2, 3, 2, 1. That's called n factorial. And you can say, wait a minute, why is this formula true? So this is basically the only formula that we need in this section. But what we need to learn is to recognize permutations and maybe to adjust the formula. By the way, formula is very easy to prove. Full proof would go by induction, but generally the idea is the following one. It's nothing else but a proof, idea of the proof at least. Easy application of the product principle. Like in one problem in the previous section. So when you choose, so here it is, you choose n elements. So first one you can choose in n different ways. Second one, you can choose everybody except the first one because no repetitions. Then n minus 2, and then the last one you have no choice, just whoever's left at the end. And their product principle says multiplied, and that's exactly what we have. So generally, this formula is nothing else but easy application of the product principle. So it looks there's nothing to learn in this section. Actually, what we need to learn is problem solving. So we'll look at the problems, recognize permutations, adjust them, and so on. So okay, this example, oh, I can erase this because it's quite complicated. You know the formula is fairly easy to memorize. I'll erase everything and start a new problem. So problem says the following. Example 4.2.1. I'm not going to copy the whole problem because you have it in my notes. So 6 people are sitting on 6 spots in a cinema, and they are labeled like seat number 1, seat number 2, and seat number 6. And then questions. Number 1, in how many ways can six persons be seated? And I'll immediately answer the questions. So what would that be? So there are 6 spots. There are 6 persons. Everybody's in, so there's seat for everybody. Order is important, nothing else is important. No person sits on 2 seats. So it's obviously permutation. So the answer is 6 factorial. That was just calling the formula. Now those little adjustments, they say the following. In how many ways can they be seated if a person A must sit on seat number 1 and person F must sit on number 6? So what happens here? No more freedom here. A must be here, and you choose whatever you want, and F must be here for whatever reason. So what happens here? No more variations here. Actually, these 2 persons just sit there, no variation there. So the only things you can kind of choose is how to seat other 4 persons on these 4 seats. So what's that? Short version of the previous problem. So it's 4 factorial. 4 persons, 4 seats. So that was easy. Now, number 3 would be a little trickier. They say, in how many ways can they be seated if A and B must sit next to each other? A and B together. But actually when they are together, it might be A on the left or B on the left. So there are 2 versions of that. So here's, we can do this problem in two different ways. One is more like tangible, the other one is more elegant and more abstract. The tangible one would be the following. All right, so I can have my AB, although it might be BA version, but let me count those configurations where A is on the left and B on the right. And then what? Now I have 4 seats like a minute ago, and these 4 other persons can sit however they want. That's 4 factorial. Then A and B here, and second and third, and here the other 4 places. How much is that? The same thing for factorial. Because these 4 persons do not care if they are together or not. 4 persons, 4 seats, all the possible shuffling. Be careful. At the end, my plan is to add up all these configurations. Do I have a danger of overlap? The answer is no, because this configuration has A and B on first and second. This one has them on, so no configuration can have A and B occupying second and third, and at the same time first and second. So there's no overlap. At the end, I can easily add up. So what then? I can have A, B here. And what would that be? 2 in front, 2 behind, and then A and B here. 3 in front, 1 behind, and A and B at the end. Doesn't matter. All of them behave the same way, so it's 4 factorial on each of them. All together, total configuration will be 5 times 4 factorial. Because 4 factorial, 1, 2, 3, 4, 5 cases, so that's or. I add 4 factorial plus 4 factorial plus 4, that's 5 times 4 factorial. And then I need to double that. Why? Because I did all that if they sit A on the left, B on the right, on those 2 seats that they get. But now there's also a version with B on the left, so this is the final answer. By the way, how much is that? 2 times 5 is 10. 4 factorial, you can get it from calculator, by the way. There is a button for factorial. Is 24, no, 4 factorial, yeah. 4 times 3, 12. Times 12, and that's 120. Correct result. No, 4 factorial, sorry. 4 factorial. There's 4 times 3 times 2, which is 24. Sorry, it's 24. It's 24. All right. Just like a solution where we kind of had transparent control of all the possible kind of groups, and then we counted each of them. Each of them is basic permutation, because those two are not hurting our shuffling of these four guys. So it was fairly easy. There's actually a much more elegant solution. And what's that? We think of AB as one big person. So basically we are shuffling one big person and four regular persons, but that's basically the same thing. So if I put big person in front, of course that big person takes 2 seats. If I put it in the middle, it takes second and third. So this is big on first, big on second, big on third, fourth, fifth. So generally what I'm shuffling is big person, which is 1, and then one big person and plus 4 regular persons. So I'm generally shuffling 5 persons. And then 5 persons, P of 5 is 5 factorial. Imagine these 2 persons like being in the bandage. But then what? But within a bandage they can do AB or AB, BA, so it's 2 times 5 factorial. 5 factorial is 120, so this is 240. We got the same answer, but look how much quicker the solution was. They're both equally good. All right. Part number 4, so they are just showing us here different ways to kind of adjust the basic problem. Problem number 4, they say what? In how many ways, if 2 of them must be separated, A and F, let's say, must be separated. We'll use that idea of the complement that we mentioned in the previous section. So total number of seatings is 6 factorial, which is 720. Number of seatings where A and F are together, we just counted that as 240. So those where they are not together, 720, you remove those that are, and that's 480. So since we already did that counting, this was much cleaner. And then number 5, in how many ways A ahead of, before B. And generally in the notes I gave you that slow solution where you kind of see, so then you look at the cases. A on first, and then you see what you can do with the others. Then A on second, and you see what you can do with the others. The only thing is B cannot be here. No, B can be A anywhere. Then if A is here, B has to be behind, and A here, then B has to be in that group, and then you need to choose one place for B, product principal, and then all the others wherever they want. So for example, if A is on second, how would that count go? There are 6 spots. And then you can say the following, all right, in how many, so I cannot call formula because B is different from others. But I'll say the following, if A is on second, B cannot be here because that's ahead of A. So B could be anywhere here. So in how many ways can I choose B? In 4 different ways, here, 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 or here. Once I choose B, let's say here, then all these 4, like other guys, I can put wherever I want, no restrictions, so it will be 4 factorial. And then when A is on third, as I said, you can see the details in the notes, but that's basically what it is. If A is here, then what? Then again, B, you need to choose one of these spots for B, so that would be 2 different ways. Once you choose B, wherever it is, these other 3 spots are for the other guys. And then finally, if A is at the end, or next to the end, then you have no freedom for B. B has to be here, and that's only 1, no, that's 3, what did I do here? I rushed it. A on second, A on third, A on fourth, no, up. Yeah, I lost 1 seat, sorry. So if A was here, and then what? If A is here, then you have 3 times 4 factorial for the others, wherever you put b, let's say here, doesn't matter. And 4 spots for the others. And then there is case where 3 behind, on number 3, then on a number 4, there are 2 of them, and that's where you get 2 times 4 factorial, and then when b is at the end, you get 1 times 4 factorial. When a is in the beginning, just 4 factorial. You add them up, and you get the result. But actually there is much better solution. Why? Because look, when you add all these numbers, I think you will get 360. But how can you get that in a little more sophisticated way to analyze this? You say the following. There are altogether 720. In some of them, A is ahead of B. In some of them, B is ahead of A. There's no, so a number of configurations where A is ahead of B is the same as number of configurations where B is ahead of A, because this condition is symmetric. A is not different from B. If they change the clothes, they change name. So each of those A configuration where A is ahead becomes configuration where B is ahead, so these must be even, so they need to split it evenly, so it's 360, 360. This is very kind of tricky solution. You're kind of, did I mess up something? Did I forget some condition? But look how quick and elegant it is. All right, let's see a little more example. There are certain type of permutation. In this part, we talked about permutation where everybody is in. But there are also sometimes we need permutation where just selected elements are in. So permutations of selected elements. So permutations of selected. So what is that? So among n elements, we only list R of them. In how many ways can we do that? Theorem says the following notation is P and R. So we have n elements, we are choosing R. Formula, you don't even need to memorize it, you can do it on your own. It's again product principle. So it's first one on n ways, n minus 1, n minus 2, and so on. But then you stop, you don't go all the way 3 to 1, and the last one is n minus R plus 1. Because if you count, there are exactly R of them. So R times you choose a new element. So this is the first one, this is the rth one, and that's the count. By the way, you can also write this if you want, and we don't need this section so much, but we'll need it maybe more in section 4.3. You actually imagine all these elements that are missing. Who's there? N minus R minus 1. 3, 2, 1. So if I had all of them, that would be n factorial. But then I need to remove the green ones, and that's n minus R factorial. So if you want a little kind of shorter formula, this is the way to write the same. N factorial, where those from n minus R down were removed. So how does that work? Next example says, for example, 4.2.2 says the following. How many 4-digit numbers exist? And then how many of them have different digits? Different digits. Before I start the problem, something that I forgot. You remember in the beginning when I talked about permutations, I answered 3 questions. And that is what? Repetition, all in and order important. So for this formula PNR, repetitions no. All in and no, some of them are in order important, yes. So for these three questions, those are no, no, yes. Unfortunately, in this example, actually, what? The solution. On the second one, let me answer the second one, I can use the formula. Why? Because here it is, I have 10 digits. And I cannot even use formula there. 10 digits, and there are 0, 1, 2 to 9. And then what? I need to choose 4. I just use product principle originally. So here it is. That's my design. 4 times I have to choose someone under restrictions. So number 1, I have 9 choices. Why? I can choose whoever I want, but I cannot choose 0 because it's not 4-digit number. Now imagine here I chose someone, like say 7, doesn't matter. No matter who was chosen. Who is available now on the second spot? Everybody, now 0 comes in, but I lose the guy that I used here, so it's 9 again. And then what? What about here? Now I cannot choose first 2 guys, so I have 8 options. And here I have 7 options. So this is the count for the 4-digit numbers with no repetition, and that will be the answer. For B, how many that we call this B part? Is what? 9 times 9 times 8 times 7, and that is 4, 5, 3, 6. What about part A? Part A actually works similar, so I'm going to just write it below the same picture, but just what happens? Still 9. So I can repeat digits, but still I cannot put 0 on first. Now what happens here? Everybody now can be used. I can even use the previous guy because repetitions are allowed. What about here? Also. Here also. So I'm not going down because what I use doesn't restrict me. So here my answer would be 9,000. Oh no, of course, I could have done it using common sense. Why? Or just counting without any combinatorics. First one of them is 1,000, and the last one is 99999. So how many is that? It's 9,000. Why isn't it 8999? Because both ends are included. I did a little exercise at the beginning of section 4.1 to just give you a little hint about counting. So if beginning and the end are counted, you subtract and add 1. So 9,000 is the total. All right, let's see, one more problem that's kind of illustrating this. And that's for example 423. It says 6 persons are seated around a circular table. So here are the seats. 1, and they are labeled. Let's say 3, or maybe not. Let me read. So 6 seats around the table. So 6 seats. And it says the following: 2 seatings are considered the same if one is a rotation of the other. How many possible seatings are possible? How many possible seatings exist there? So here is probably the best way to do this problem. I can seat the first person in any of these 6 seats. But imagine that I can rotate the table. So if I seat the person 1, wherever I seat the person 1, or person A, let's say, person A, where do I seat it doesn't matter. Why? Because I can rotate the table. Let's say that there is a mark on the table. Here there is a little star. So I can always rotate the table so that the star points to that person. So if he sits here, I'll just rotate it because rotations are allowed, so those are considered the same seatings. So here, I'll put my A here, and I don't count times 6, because as I said, that's only one option. So A is the one that gets the star through the rotation. From now on, I cannot rotate because that's the limitation. And now what happens, I can put B, C, D, and E wherever I want, so the answer would be 5 factorial. And that's it, very quick. Or, the other way, I like this one, it's very elegant. Or you can do the following, you can take 6 factorial, is total, because 6 persons can sit on 6 chairs in 6 different ways, like in the theater. But now what? I will divide by 6, because all those configuration where A is here count the same way as the appropriate configuration where A is here, 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 because I can get them with the rotation. So that's why each of them was counted 6 times. So I divide, and I get again, it's 6. Oh, by the way, in calculations, you'll see that we'll need that very often in section 3. 6 factorial is 6, 4, 3, 2, 1 over 6. So very often we write this 6 times 5 factorial. First times all the others, then this cancels, and I get 5 factorial.